Hello everybody, and welcome to our video on optimization problems. So this is going to be another very application-centric section. So we're looking at a basic process here for these real-world problems. First, understand the problem. Figure out what are your unknowns, what are your given quantities, what are the conditions, list them out. Draw a diagram. All right, you're usually going to need some sort of picture to figure out the relationship of your variables. Introduce your notation, so assign symbols to what is going to be maximized or minimized. Select symbols for your other unknown quantities. Label your diagram. Express your quantity in terms of one of the other symbols. Find a relationship between your quantity and any other variables. And finally, use the information from our previous sections to find the absolute maximum value. Okay, so reminder, you can use the second derivative test to verify that something is a local minimum or maximum. So when you solve these problems, typically you need to verify whether or not the thing that you've actually found is a maximum or a minimum. Now sometimes you can work through the real world reasoning, like maybe it's only possible to have a maximum or minimum based on the conditions at hand, but usually it's faster to actually just apply the second derivative test here. So let's start by taking a look at this first example. Find two positive numbers whose product is 100 and whose sum is a minimum. This is a rare example where there's not much picture you can draw here, but we can directly write out the equations that are being described here. So two positive numbers, so x and y, whose product, x times y, equals 100, and whose sum, x plus y, is a minimum. So we can call this our, well, we labeled it Q in the description above, so let's just label it Q here for quantity. So whose sum is a minimum. So the first thing I need to do is get things in terms of, get my quantity that I want to minimize, in this case, in terms of one variable. So I'm going to do that by substituting y in place of a function of x, and that's where this constraint comes from. When we're looking at these optimization problems, you're always going to have some kind of constraint in place. The constraint is a relationship between the variables that's some fixed value, a fixed relationship between them. And you need to use that constraint to actually write the quantity you're maximizing or minimizing in terms of one variable. So that being said, here I can just set y equal to 100 divided by x and substitute that into my quantity. So q equals x plus 100 over x. And I'm just going to rewrite that as x plus 100 times x to the negative first power. That way I can take my derivative a little easier. So that's going to imply that the derivative of my quantity is 1 plus 100 times negative 1 times x to the negative second. That's 1 plus 100, I should say 1 minus 100, over x squared. Okay, so in order to find a maximum or minimum, we need critical values. So q prime equals 0 implies 1 minus 100 over x squared equals 0. Move the 100 over x squared to the other side, I get 1 equals 100 over x squared. So of course that means x squared equals 100. Take the square root, and you get x is plus or minus 10. But negative doesn't make sense, so it's got to be positive, right? We're looking at two positive numbers, so we're only looking at x equals 10. So x equals 10, and then what would y be equal to? Well, we can go back to our constraint equation and solve y equals 100 over 10, so that's 10. Okay, but we want to actually check if this thing is a minimum, so we're going to verify here. How am I going to do that? Well, I'll just do the second derivative test. Take the second derivative of this function. So here I'll rewrite q prime as 1 minus 100 x to the negative second. So when I take my second derivative, I get negative 100 times negative 2 x to the negative third. That's 200 over x cubed. And since x is restricted to being positive, that tells us the second derivative is positive. So that tells us it is a minimum, right? When the second derivative is positive, that means it's concave up. So the point we're looking at is a minimum on the graph. All right, that's it for that one. Let's go ahead and move on to another example. So a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. So he's got a river here. And then the rest of it, he just wants to be a rectangle. So let's say this unit is x and this is y. What are the dimensions of the field that give the largest area? Okay, well, what's the area? Oh, it's x times y. But he has 2,400 feet of fencing. So 2,400 is my constraint, and it's a constraint on the total length here. I've got 2x and 1y. So 2x plus y is 2,400. Now, what do we want to maximize? We want to maximize the area. So I'm going to need to do a substitution into my area function. And so I'm going to replace y, since I've got y to a single power here and there's nothing multiplying. It's just a little easier. 2,400 minus 2x equals y. So that implies that a can be written as x times 2,400 minus 2x. And that's 2,400x minus 2x squared. So now, take the derivative. I find my critical numbers. So my derivative gives me 2,400 minus 4x. So this derivative is 0. Implies that 2,400 minus 4x equals 0. I move the 4x across. I divide by 4. And I get x equals 600. So that's x equals 600. And if we plug that back into our constraint for y, that tells me y should equal 2,400 minus 1,200, which is 1,200. But I want to double check that this thing is actually a maximum. So we take the second derivative. So we're verifying that this is a maximum. So the second derivative is just negative 4. Oh, well, that's negative. And if the second derivative is negative, that means this thing is concave down, and so it is a maximum. So yes, it is a maximum. And keep in mind here, what we've been asked are, what are the dimensions? A problem might ask you, what is the largest area? That's not being asked here. But if they ask that, then you would need to actually multiply x and y for that final result. All right, let's move on to another example. A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay, so let's draw a picture. We've got a can. It should look something like this. Now, we are making some assumptions here, but we're going to assume that the metal on the top, bottom, and sides is all the same thickness, same metal in general, which means that minimizing the cost is equivalent to minimizing the quantity of the metal. And what is the quantity of the metal? Well, here we've got a radius, right? And it's going to be the same radius up top and bottom. So we've got 2 times the area, pi r squared, of the top and bottom. And then we also need the area of the can. And so, you know, sometimes we'll draw what we call a net diagram. You may remember these from a long time ago in ye old middle school. So when we draw this, we've got the height of the can here. It's like we've cut the can and unrolled it and flattened out the side, right? So what is the length here? What's the circumference of the circle, right? If you slice this down the side and you unroll it, this length is the circumference. And the circumference is 2 pi times the radius. So the area of this thing is 2 pi times the radius times the height. So we've got to add 2 pi times the radius times the height. Now, what's our restriction? The cylindrical can only hold 1 liter of oil. Okay, so how do we get 1 liter of oil here? Is 1,000 centimeters cubed. Okay, so now that we've got that, well, that tells us also we should be working with centimeters for our radius and our height, so forth and so on. So, all right, let's go ahead and go from there. So 1,000 centimeters cubed is our volume. And what would the volume be? Well, that's the height times the area of the base. So that's the height times pi r squared. And this needs to be equal to 1,000. So we need to do a substitution from our constraint into our quantity. So we get h equals 1,000 divided by pi r squared. And we'll plug that right in. So our quantity becomes 2 pi r squared plus 2 pi times r times 1,000 divided by pi r squared. Do a little simplification here. Pi over pi cancels. R over r squared becomes just 1 over r. So this becomes 2 pi r squared plus 2,000 divided by r. Now I'll rewrite that slightly again as 2 pi r squared plus 2,000 times r to the negative first power. So now we'll take our derivative. Q prime is going to be 4 pi r minus, because the derivative of r to the negative first is -1, r to the negative second. So minus 2,000 r to the negative second. And now to set this thing equal, I'm really going to equal to 0. I'm really going to have to rewrite it. 4 pi r minus 2,000 over r squared. And I'm going to want to find a common denominator. So I'm going to multiply r squared top and bottom here. So this gives me 4 pi r cubed minus 2,000 over r squared. Okay, so when does this derivative equal 0? When the numerator equals 0. All right, let's solve for it. That gives me 4 pi r cubed equals 2,000. Divide by the 4. I'm going to get pi r cubed equals 500. It's going to give me r cubed equals 500 over pi. And finally, r equals the cubed root of 500 over pi. So that's my value for r. It wants both dimensions though, so we've got to use our restriction to find the height. So here's r. So the height is 1,000 over pi times r squared. And I'm going to leave that value as is. Now, as for verifying that this is a minimum, now you could plug this into a calculator, get an approximation. Again, I'm not going to bother doing that. That's easy. Just plug into the calculator. But let's take the second derivative here. We get 4 pi plus 2,000 times 2 r to the negative third power. And of course, we're assuming r is a positive value because the dimension doesn't make sense to be negative. So that tells us that this is strictly positive. So if it's strictly positive, then that verifies that this is a minimum. Okay, let's go ahead and move on to another example. All right, so as a reminder, the first derivative test says that you can check the derivative on either side, and if the derivative goes from being positive to negative, it's an absolute maximum at that critical point. If it goes from negative to positive, it's an absolute minimum. So with these optimization problems, you might, for a given problem, prefer to work with the first derivative instead of the second if the second derivative is overly complex. All right, let's go ahead and take a look at this one. Find the point on the parabola y squared equals 2x that is closest to the point 1, 4. So just to draw this picture here, 1, 2, let's see, we want the point 1, 4. So the point we're concerned with is here. And the graph, y squared equals 2x, is a right-facing parabola. So when x equals, say, 2, then I get y equals 2 as well. And when x equals negative 2, I could also get y equals negative 2. Right, I get y squared equals 4, so y could be plus or minus 2. And this graph looks like this. So we're looking for the point that's got like the shortest distance here. What's this point, right? So something like that. I don't know exactly where it is on the graph. My picture is not to scale. But somewhere in that vicinity is what we're looking for, just to get an idea. So what are we trying to do? We're trying to minimize the distance. But distance is a little bit hard to minimize because you've got the square root of, in this case, x minus 1 squared plus y minus 4 squared. And taking a derivative with that square root and squares inside, that's all a mess. So really, I'm going to minimize the distance squared. Makes this problem a lot simpler. And whatever minimizes the distance squared is also going to minimize the distance. So that's going to be a lot easier for us to work with. Now, what constraint do we have? Well, the constraint is the parabola itself, y squared equals 2x. So we can replace x with y squared over 2. So in this case, our d squared becomes y squared over 2 minus 1 squared plus y minus 4 squared. So now when I take my derivative, I get 2 times y squared over 2 minus 1 times 2y over 2. That's the derivative of the inner, just applying the chain rule there. And here we get 2 times y minus 4 times the derivative of the inner function y. Now remember, this derivative is with respect to y here, so it's just 1. All right. Now we gotta do a little bit of cleanup here, a little multiplication. So distribute this 2 here, and we get y squared minus 2 times 2y over 2, which is just y, plus 2y minus 8. And so what does this give us? We get y cubed minus 2y plus 2y minus 8. Those cancel. So I get y cubed minus 8 is the derivative, the distance squared's derivative. Okay, so when is this derivative 0? That implies y cubed minus 8 is 0, and so y cubed equals 8. and so y is plus or minus 2. But of course, we can look at the picture and immediately discount the negative option, because obviously that's any y value that's negative is going to be much farther away than any point on the top half of the curve. So we can immediately just jump to y equals 2. And if y equals 2, we plug that in here, we get x equals 2 as well. Well, I tried to be a little deceiving with the picture and not just draw the line straight to 2, 2, but it is that exact point. Now, we do want to verify that this is a minimum. So we could do the first derivative test, right? But if we look at our first derivative, y cubed minus 8, if we look at, let's say, the derivative at 1 for y, we get negative 7. And if we look at the derivative at, let's say, 3, we get 27 minus 8. That's going to be 19, I mean. So we go from negative to positive, so that tells us that, yeah, it is a minimum. Okay. Well, that's it for that example. Let's go ahead and move on to one more. I believe this is our last one. Yeah, this is our last one. If 1200 centimeters squared of material is available to make a box with a square base and an open top, find the largest possible volume of the box. So, you got a square base. That means the side lengths are the same. But the height could be different. Now the key part here is the top is open. So when we're looking at the material, we're just looking at the area that each of the sides takes up. So that 1200 centimeters squared only accounts for the 4 sides and the bottom because the top is open. So we need a height here. And so what do we see? Well, the bottom is x squared. And then we have 4 sides, and each of the sides is going to be x times h for area, right? So that's going to be 4 times x times h, since there's 4 sides. And now we want to make the largest possible volume, but the volume is the area of the base times the height. So when I look at this, I look at my constraint. I want to substitute h into here, so I have a function of just x. So we get 1200 minus x squared equals 4xh. So 1200 over 4x minus x squared over 4x equals h. So h is, let's see, this is 300 times x to the negative first power minus x over 4. So when I plug this into my volume, I get x squared times 300x to the negative first minus x over 4. That gives me x squared times x to the negative first is just x minus x cubed over 4. And now I can take my derivative. So my derivative here is 300 minus 3x squared over 4. And now we can set this derivative equal to 0. So we get 300 minus 3x squared over 4 equals 0. So 300 equals 3x squared over 4. Multiply the 4 across, that's 1200. Divide by 3, that's 400. Equals x squared. So x equals plus or minus 20. But again, this is it's a real world problem. We're looking at positive lengths here. You can't have a negative length of a box. So we're just looking at x equals 20 here. So x equals 20. And what is h then? Well, let's look at this form for h. We have 1200 over 4x minus x over 4, right? So 1200 over 4 times 20 minus 20 over 4. That's 1200 divided by, let's say, over 4. That's going to be 300 divided by 20. It's 15 minus 5. That's 10. So h is 10. And so the largest possible volume should be 20 squared times 10. That's 400 times 10. That's 4,000 centimeters cubed. But we should go ahead and verify that this is indeed a maximum. So if we take a look at our derivative, I think I'm going to go back to the second derivative test here, because then I just get negative 6 over 4x. And for positive values of x, this is negative, so it's concave down. So this confirms it is a maximum. So let's take a look at this example now. A rectangular storage container with an open top is to have a volume of 10 meters cubed. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest such container. So first, let's just try to draw this container. So it's a rectangular storage container, so we'll draw like the front side of that first. Okay, and let's try to get some of our information on here. We know the length of its base is twice the width. So this is 2x if the width is x. Now we also need a height, and there's no particular restriction mentioned for the height. Now it says it's got an open top, but it's to have a volume of 10 meters cubed. Well, having an open top doesn't affect the volume, so let's just look at the volume here. So that's going to be length times width times height. So 2x times y. That's 2x squared y. And we know that this volume has to be 10 meters cubed. That's the restriction. So this is our constraint. Okay, so now we want to figure out how much the material is going to cost. But in order to do that, we first have to figure out how much material is needed for the base and for the sides, respectively. So we're going to draw a net diagram here. So that's like if we cut along the diagonals of our box and we folded out the sides. So what do we get? We get something like this. The bottom, so imagine this is a top view. The bottom of this box is going to look like dimensions 2x and x here. And the sides should all have height y. And so now let's just label the areas of each of these parts. So the base, 2x times x, that's 2x squared. This will be xy. This will be xy. And this will be 2xy. And this will be 2xy, right? We're just multiplying the length times the width for each of those rectangles. So now, let's take a look at the base material. How much base material do we have? Well, that's just this part in the middle. 2x squared. And how much side material? Well, that's all of these components here. We've got 2xy plus 2xy, that's the two long sides, plus the two other sides, xy and xy. So I've got 4xy, 5xy, 6xy. Okay, so then what is our cost going to be? Well, it's $10 times the amount of base material plus $6 times the amount of side material, which is 6xy. So we can simplify that a little bit, make it 20x squared plus 36xy. So now, in order to try to optimize this, we need to be able to take a derivative, and we want to reduce this to one variable instead of two. So I'd like to essentially get rid of this y. Well, if I go up to my constraint equation, I can solve that for y. I can divide my 2x squared across. I get 10 over 2x squared, which is 5 over x squared. So that's easy enough. And then I'll take this and plug it back into this value over here. So that makes my new cost formula in terms of only x, 20x squared plus 36x times 5 over x squared. And if I rewrite this a little bit, 20x squared plus 36 times 5 is going to be 180. And x over x squared is x to the negative first power. So now I've got my cost equation. And so now I can start actually working to minimize the cost, right? We want the cheapest such container. So we take our derivative. That's 20 times x squared. That's going to give us 40x. And then 180 times negative 1. So that's negative 180 x to the negative second power. And of course, we want to set this equal to 0 and solve it. We'd also like to find out where the derivative doesn't exist, but the only place that's going to happen is when x is 0. Because if we rewrite this 180 over x squared, you can't divide by 0. But that's not a problem in the context of this problem, because you can't have a 0 length for a side of your box. So we can ignore that case for this particular example. Okay, so we want c prime to be 0. I'm going to rewrite that as 180 over x squared instead of x to the negative second. Okay, we'll move our negative term to the other side. We get 40x equals 180 over x squared. We'll multiply by x squared and divide by 40. That gives us x cubed equals 180 over 40. So this gives us x cubed is, that's going to be 9/2. So finally, x is the cubed root of 9/2. Now the question said, what is the cost of materials for the cheapest such container? So now we have to take this value for x and plug it in. Now technically, we haven't shown that this is a minimum yet, but I'll do that at the end, right? Technically, you know, we don't really know until we've done one of our tests to see if it's a minimum or maximum. But I'm going to just go ahead and finish that part out, and then we'll do a little aside checking that it is, in fact, the minimum. So now we're going to evaluate our cost at the cubed root of 9/2. And so for this, I'm going to use the version of the cost formula we found that was strictly in terms of x. So 20x squared plus 180 x to the negative first, which is 1 over x. And if we plug that into a calculator, we get that this is approximately $163.54. Now, as far as checking that it's a minimum, We can do that pretty quick, right? So if x, let's pick an x value that's smaller than the cubed root of 9/2. Well, obvious one is just 1, right? 9/2 is bigger than 1, so even the cubed root is bigger than 1. So we'll just go with x equals 1. And what does that tell us about the derivative? I'm going to get 40 minus 180. That's definitely negative. And let's pick a value larger. So we want something, I take the cubed root bigger than this. How about 8, right? So yeah, 8 should be bigger than that. That's got to be smaller than 8. Because the cubed root of, let's see, cubed root of 9/2, it's way smaller than 8. Because that's 3.5. So that should be fine. We could go above that if we wanted, but not necessary. So if I do that, what do I get? Well, get 40 times 8 minus 180 over 64. 180 over 64 is about 3-ish. So I'm going to get 40 times 8 minus about 3-ish. So that's definitely going to be a positive value. So that's good enough. Okay. That confirms it, right? The derivative goes from negative to positive, so that's a minimum. All right, let's move on to another example. So this is kind of a tricky problem, and as with many of these sorts of optimization problems, there's often several ways that you could approach this that are all perfectly valid, but sometimes one way is just a little bit easier or less cumbersome algebraically than another. So if you were to try this problem on your own and try tackling it in a different way, and you found a way that works and gets you the same answer, that's totally fine. There are many ways to do this problem. I'm just going to take this one. Okay, so a right circular cylinder is inscribed in a cone with height h and base radius r. Find the largest possible volume of such cylinder. So the first thing I got to do is draw these things. So we want a cone and a right circular cylinder inscribed in it. Inscribed means it's inside of the cone, but it's stretched out to the edges, essentially. So like this. Now, normally, when we think about the volume of a cylinder, it's going to be the height times the base, the area of the base, which is, of course, what we're going to use. But we're going to have to somehow write that in terms of one variable only. So that's where things get a little tricky. When we look at this cone, we know that it's given that the radius of the cone is r, and the height of the cone is h. So what I'm going to do here is think about similar triangles, because I'm trying to find a relationship between the cone and the cylinder. And so if I imagine drawing, let's pick purple here. If I imagine drawing a perpendicular line through the center of the cone and the cylinder, I get a right triangle that goes out to the edge here. The picture's not perfect. But I also get another right triangle here where the cylinder meets the cone here. And so there's some sort of relationship between these two triangles. So let's redraw those triangles out here. So this whole thing, this whole side is h. This is r. And so I'm just going to give labels to these short sides for the short triangle. We'll call the top one y, and the bottom one we'll call x. And so we know from the similarity of triangles that y over x equals h over r. Okay, so that's just a fact of the similarity of triangles. If you have two triangles that are similar, the ratios of their corresponding sides are equal. So y over x is equal to h over r. Now, why do we know that these triangles are similar? Well, we know they're similar because they're both right triangles. They both share this angle, and that means the third angles have to be congruent as well. And when all three angles are congruent, then the two triangles are similar. Okay, so y over x equals h over r. That gives me a relationship between the parts of this triangle. But that's not quite what I need, because what I need is a relationship for the cylinder. So the setup part here is tricky, but once we get it, hopefully you'll see that this, using this similar triangle, actually makes the calculus part of the work pretty easy. So I now have to figure out how to describe the height and the radius of the cylinder in terms of y and x and h and r. So if I look at the height of the cylinder, it's the height of the cone minus this y portion up here, right? This little part y. So this height is h minus y. And of course, this x here is actually the radius of the cylinder. So that makes things a whole lot easier, because now I can say my volume for my cylinder is my area of my base, which is pi x squared, times the height, which is h minus y. Now, h is a fixed value, so I don't need to worry about replacing that. I only have to worry about getting rid of any variables, any things that change value, which is y and x. So I need to reduce this to one variable. So if I go back to my similarity of triangles equation, this is my constraint. This is what relates my x, y, h, and r values. And so I can rearrange that and make y equal to hx over r. And then I can take that value and plug it right into my volume for a cylinder. Okay, so that's my volume so far. Now I just need to rewrite this in a little bit nicer way so that I can actually take a derivative with it. So if I multiply this out, pi times h times x squared, pi hx squared, minus, and then here we've got pi h again, x squared times x, that's x cubed, over r. Now, this function, when I take its derivative, gives me what? I've got x squared here, so that's 2 pi hx minus, and then this is x cubed, so that's 3 pi hx squared over r. Now, I want to check when this is equal to 0. I also need to check when this derivative doesn't exist, but in this case, this derivative exists everywhere, right? We've just got x and x squared, so there's no problems there. So when is this derivative 0? Well, I'm going to go back up here and rewrite this derivative a little first. I'm just going to factor out the common things. I've got a pi and an h in both of these, and I've got a factor of x. So we're going to pull out the pi hx. And then that's going to leave us with 2 minus 3x over r. So now, when is v prime 0? Well, it's when pi hx is 0, or 2 minus 3x over r is 0. But in this first case, if pi hx is 0, that means x is 0, and this again would be a silly, trivial case, because we're obviously not talking about a cylinder with radius 0. So we can exclude that. Now we add the 3xr to the other side for the second equation. I get 2 equals 3x over r. Solve for x, multiply the r, divide by 3, and we get x equals 2r over 3. Now, of course, the question was to find the largest possible volume of this thing. So we're going to have to take this value for x and plug it into the volume formula. And of course, we're going to use the volume formula that we wrote strictly in terms of x. We can use this one here at the end. Pi h times 2r thirds squared minus pi h over r times 2r thirds cubed. This becomes pi h times 2r squared, that's 4r squared, over 3 squared, which is 9, minus 2 cubed is going to be 8. Put that in front. 8 pi h r cubed over r times 3 cubed, which is 27. And now we do a little bit of cleanup here. We've got r cubed over r, that's r squared. I'll write this 4 out in front. This is 4 pi h r squared over 9 minus 8 pi h r. Oh, that was supposed to be r squared. I wrote r cubed again. Sorry about that. That should be r squared over 27. Okay, so now I need a common denominator because I've got pi hr squared, pi hr squared. If I just had a common denominator, this would be easy. I could multiply by 3 over 3. It's 12 pi hr squared minus 8 pi hr squared over 27. And if I have 12 pi hr squared minus 8 pi hr squared, that's 4 pi hr squared over 27. Okay. Well, that one's a fairly tough problem, I think. But once you get the setup figured out, the rest is just the general kind of standard stuff that we do in these optimization problems. Well, that's it for this video. Thank you for watching.